Hello to all of you. So now let's do design of deck type brace. The problem is in deck type plate girder is to provided for single meter gauge track and a standard mainline loading. This is the question, and also designed to according to bridge rule. Following data are given: span of girder 24 meter, self weight of stock rail 0.8 kilonewton per meter cube, cell weight of god rail 0.4 kilonewton per meter cube, spacing between girder. What is the girder? Which is just underside of sleeper. This is girder, and the spacing center to center, which is 1.3 meter, and weight of fastening 0.2 kilonewton per meter sleeper, at which is the spacing 0.4 meter of sleeper between two sleepers, and the size of sleeper is 2 meter into this is 2 meter size, this is 250 which is width, and this is height 250 and the density of the sleeper material, which is timber here, that is 7.5 kilonewton per meter cube. Now let's have to start designs, and the step number first is calculation of loading. Then we will calculate first to dead load. What is dead load? Dead load is the sum of the spacing self weight of stock rail, self weight of god rail, weight of fastening, and about to sleeper also. Okay, now weight of stock rail, how it will calculate, I have also told you in the design step. You have to multiply by 2 into stock rail plus god rail. What is the value of these two? 0.6 and 0.4. You can often this is 0.6, and by mistake this is written as 0.8. okay, 0.6 and 0.4, it will 2 kilonewton per meter. And now weight of fastening, it was also given here, weight of fastening 0.2 kilonewton per meter cube per meter, then it will written here same as, and weight of sleeper, which is volumetric density upon spacing. Then we will use all the three values of only sleeper. If here is spacing, we will use spacing 0.4 meter, not to spacing of the girder 1.3 meter. You have to understand, but must you have to use only 0.4. Then we will use 0.4 spacing. How we will calculate volume is of this sleeper material is 2 meter into 250 into 250 then it will 2 meter into 250 into 250 that is 0.25 in the meter. And density we will also find out from here. Density of the timber, which is sleeper material, is 7.5. we will write here this, and we will find out by the calculation 2.34 kilonewton per meter. So how it will calculate dead load? Then total dead load will be all the sum of these 2 plus 0.2 plus 2.3, 2 plus 0.2 plus 2.3 into span of girder, which is 24. Now it will 108.96 kilonewton. Okay, now we will calculate live load. How it will calculate? We have to visit page number 28 at appendix 4 in the bridge rule. Now yet I didn't have to present you, but I can tell you for bending moment from the page number 28, it is 1625.9 kilonewton. You will get easily when you will visit this page, and it will vary by this span of girder. If this is 24, then we will take these two. Okay, this is 1767.2 kilonewton, and at the C we will find out impact load. We have discussed also about impact factor to find out impact load. What is impact factor? We have a formula to find out this. Impact factor is 0.15 plus 8 divided by 6 plus L. if you will find out these two, you will also find out their impact factor. If you wanted to choose that impact factor, then you have not to calculate this. But if you don't want to choose that, you can also calculate. Then you will find out this is 24, and you will calculate, and it will 417. Okay. Now impact load for bending moment. It will impact load depend upon to live load. So impact factor into live load for bending moment. Then what is impact factor? 0.417. What is live load for bending moment? Live load for bending moment 1625.9. 1625.9, and by the calculation this is 678.003 kilonewton. And we will also evaluate impact load for shear force, which is impact factor into live load of shear force. And how will you get? Impact factor is 0.147, and impact load of shear force 1767.2. This is 1767.2. Now it will 736.92 kilonewton by the calculation. And step number D is discussed also in previous video: self weight of main girder. Self weight of main girder, which is WL by 300. What is W? W is total load plus live load for shear force plus live load for impact loads or shear force. Okay, then what was total load? I will just see you. Total dead load was 108.96. Okay, 108.96 plus live load for shear force. We will visit live load for shear force 1767.2, and impact load for shear force. Impact load for shear force is 736.92. Okay, now this is 2613.08. Okay, now we will find out WL by 300, which is here 2613.08 into 24. Here is no need to multiply by 10 to the power 3, because this is finding out within kilonewton per meter. 8.74. This will 8.74 multiply by 24, it is 209.04 kilonewton. Okay, now we will write that self weight of main girder is is 209.04 kilonewton. We just have to obtain. Okay, hence total dead load will be what will 209.04 plus dead load in the step number first A 108.96, and total dead load will be 318 kilonewton. Okay, now we have to draw a table. These are loads, these are for bending moment and for shear force. Okay, now loads, what are the loads? Dead load, live load, impact load, and calculate total load. Okay, what are the dead loads? 318. It will assumed as a dead load for bending moment and for shear force both. have already told you in the design steps. Okay, so this is 318 and 318. What is live load? Live load, I just wanted to tell you, live load 1625.9 and 1767.2. तो 1625.9 or 1767.2. okay, and impact load we also have calculated. Impact load for shear force and impact shear force and impact for bending moment. Okay, now we will write here 678.0034 for bending moment, and it was 736.92 for shear force, and the total dead load is two. Total loads or for bending moment is 2621.90, and this is 2822.12. And now step number E is load per track. We will also evaluate the load how much on single track. Okay, for bending moment this total load will be half 2621.90 divided by 2, it will 1310.95 kilonewton, and for shear force it will 2822.12 divided by 2, which will 1411.06. okay, now we will find out step number 2. What is step number 2? Step number 2 is the calculation of shear force and bending moment. Calculation of shear force and bending moment. Okay, we will find out M equals to WL divided by 8, and what is W? W is here bending moment 1310.95. 1310.95, this is W of M. Bending moment into L is 24, span of girder, you can see here span of girder 24. okay, divided by 8. Now the value of this will be 3932.85. you have to remember this, it will use many times in many designs steps in the next steps. okay, also I found out to shear force. Shear force will be W divided by 2. what is W? W is here 1411.06 for shear force, because we are evaluating shear force. okay, this is 1411.06 divided by 2, which will 705.53 kilonewton. okay, now we will find out step number 3. Step number 3 is calculation size of web plate and economical depth. okay, calculation size of web plate and economical depth. Then assume thickness TW equals to, I'm not writing to the step because it will be decrease the time. okay, TW equals to 10 mm and D equals to 1.1 into bending moment divided by sigma B into TW. This is the formula to find out economical depth, to power 1 divided by 2. Now what will sigma V? Sigma will V, I want to tell you, this is 0.66 Fy. you can find out from here to sigma B. 0.66 Fy is 250, and this will 165 Newton per mm square. You have also to remember this, it also be used in next steps moreover. So we will find out D. 1.1 bending moment is 3932.85. we will also multiply to this by 10 to the power 6 divided by, we will find out this value in mm, so I multiplied by this. okay, 165 into 10. what is 10? 10 is TW, which is assumed. okay, to the power 1 divided by 2. Then we will find out D equals to 1.698. okay, which is in meter, and will change 1698 mm. we will take D equals to 1700, which is nearest of 1698 mm, no matter what we obtain to nearest value. Okay, B provide 1700 mm into 10 mm wave plate. Please remember this for the next steps, it will used many times. Step number 4, calculate of size of flange. Okay, net area flange in tension, what it be? Net area flange in tension, that is A dash ft equals to maximum bending moment, that's M, and sigma b into d. Sigma b have obtained 165, and d is lever arm, okay, which had here 1700. Okay, now we will find out what is M. 3932.85 into 10 to the power 6 divided by what is sigma b, 165, and what is d, it is 700. Then we will find out A dash ft, 140.20.85 mm square. Okay, now we have find out A dash ft, sorry, we have find out A dash p, okay, which is net area of flange plate. We know the formula of this, 2 by 3 A dash ft. You can watch to derive this formula in the design steps discussed already in design steps. Okay, so A dash p equals to 2 by 3 A dash ft have evaluated 140.20.85 minus 8, what is AW, 1700 into 10, already told you have to remember this one. Okay, divided by 8. We will calculate this value. A dash p, what is A dash p by the calculation? 7222.23 mm square. Maybe a little bit mistake in calculations, but the steps or design technique will not change. Okay, also we will find out gross area for plate. I have already told you in design steps we will increase 120% of this area. So gross area for plate, it will 120% divided by 100 into A dash p. What is the value of A dash p? This is 120 divided by 100, that is 1.2, and this is 7222.23. Okay, now it will 8666.68 mm square. Okay, and also find out net area for angle 2. Net area for angle 2, this is 2, that means V. This will also increase 120%, that is 1.2 into A dash. What is A dash? This is net area of flange angle section, and it is A dash ft divided by 3. I have also told you in design step, if you have watched you will not get a problem to face. Okay, 1.2, and we have also find out this A dash ft, which was here 140.20.85, then 140.20.85 divided by 3. Okay, 5608.34 mm square. This is also net area for planes too. Okay, now for one angle area, what it be? Now for one angle area you have to write here complete for one angle area. This is for 2, then we will divide by 2 to get the area of one angle. Okay, 5608.34 divided by 2, which will 28.04 divided by 18. Okay, mm square. Now we will draw a diagram in the design step I was trying to draw a diagram to understand this, but that was failed. Now I am trying again. Okay, that was not failed, that was bad in look. Okay, so now it have been drawn, and we will also drag here to look supports. Okay, now this is drawn, and we will choose a section. I am choosing this section by my own thinking. 150 into 115 into 12, you will get it at steel table, table number 7. Table number will be 7, and page number I will also told you 24. This is table number, this is page number. Okay, now 2 plates of 400 by this section. One, I say 150, 115 and 12. This is 400 and this is 12. It also be 12, it also be 12, it also be 12. Okay, and now this is 1700. Okay, then let's start. 2 plates of 400 into 12. Okay, 400 into 12 provided. We can also write like 2 at the rate 400 into 12. Everybody can understand by this. Then 2 angle 150 into 115 into 12. We will find out the area from the steel table. It will 3038 mm square. Because this is the 2 angle, we will write area for single angle. Okay, it will in the table 06076. In the table we will divide by 2 and we will get this. Okay, and we will also write Ixx, moment of inertia, from there. This will be there 1353 into 10 to the power 4, but we are writing here for the single angle. Then we will write the half of this, 676.5 into 10 to the power 4 mm ki power 4. Okay, and Cyy also, it will 2.90 there. Then we are writing, there is in the meter, and we are writing for the mm, this is 29 mm. In same table you will find out also this. Okay, now step 5, this is the last step, to check for stresses. Okay, first is bending stress in compression flange. Bending stress in compression flange. Okay, now we will, according to design steps, sigma cbc, find out m upon I dash xx into y. What is y? I already told you. Sorry, I didn't told, I am telling you. This is 1700 plus 12 plus 12 plus 12 plus 12 divided by 2 to get center of gravity of the whole section. Okay, 12 12 1700 12 and 12, and we will get this maybe here or anywhere divided by 2, and it will 874, half of 1748. Okay, this is y. And also have to find I dash xx. Then we know bd cube. Then here is b 10 and d is 17. 100 cube divided by 12, and also plus 4 into Ix of section plus area of section into 1700 divided by 2 minus Cy to the power 2 bracket close plus 2 BD cube of the bed plate, which was 1400 into that was 12 24. Okay, 400 into 12 plus 12 24 cube divided by 12 plus 400 into 24, this is area, into 1700 divided by 2 plus 12 square. If you know to how to calculate moment of inertia, you can understand easily, and we will put all the values I dash xx. Okay, then we will write 10 into 1700 as it is of the above divided by 12 plus 4 into what was ixx, 676.5 into 10 to the power 4. You can see here, this is 676.5 into 10 to the power 4. Okay, and what is area? Area is also 3038. Okay, 1700 divided by 2 minus what is Cyy from the code is 29. Okay, 29 to the whole power of 2, and plus 2, 400 into 24 to the power 3 divided by 12 plus 400. I will calculate this in a single term to all the values. Okay, add in the calculator. You have to also use calculator, and we will find out this value to 6.58 into 10 to the power 9. You can also obtain 2.658 into 10 to the power 10. Okay, there is no problem if you will find out there. Okay, now this is the value of ixx, and this is value of y, and we know what is m was 3932.85. I told you to remember that. If you had not remember, I wanted to show you this. Okay, 3932.85. and now we will find out sigma cbc, characteristic compressive strength. Then what is m? 3932.85, and we will change this in Newton mm. Okay, and 875 the value of, sorry, it was 874 the value of y, and divided by r dash xx, this is 26.58 into 10 to the power 9. Okay, now sigma cbc by the calculation will be 129.47, which should not be exceed from the sigma b. What was sigma b? Sigma b was 165. If you didn't have remember, I just wanted to show you what was sigma b. Sigma b was 165 in step number 3. Okay, now it is shown that safe. Okay, safe. Then step number 5b. Okay, check for bending stress in tension flange. Check for bending stress in tension flange. This is not compression, this is tension. Okay, so we have to evaluate sigma vt, which will calculate by sigma cbc into af plus aw divided by 6 a dash f plus aw divided by. Okay, so we will draw a table in the 4-part section: gross area, reduce net area. So at first, what are the sections to? At first we will consider two flange plate of 400 into 12. Okay, and the next section to ISA 150 into 115 into 12. Okay, web plate 1700 into 10. These are two area. You have to calculate the gross area and net area. Net area, how will it will calculate? By the reducing area from the gross area will be net area. Okay, so how? Gross area is 2 into 400 into 12. And what will be reduced? We will reduce the area of the bolt hole. Okay, diameter of the hole. Okay, now 200 into 4 into 12, it will 9600. And what is this? It was 607. It was 6076. We will not take for single, we will take all over. 6076 it was. And web plate 1700 into 10. 1700 into 10. For the gross area, this is the gross area, so here is 6 divided by 6. Okay, what are reducing? What have to reduce? Assume size of bolt, diameter of bolt dB is 22 mm. Then what will diameter of hole be increased to mm for this? Then it will 22 plus 22 2 plus 20 22 plus 2 24 mm. Okay, so we will assume the how many will be holes. Okay, now we have to understand from the diagrams. As we will add 1 volt here, 1 volt here, sorry, 1 volt will be here, and 1 volt will be also here, 1 volt will be here, and 1 volt also will be here. So you can see this 2 volt, 2 volt, 4 volt for 4 volt for web plate, and 2 volts for flange. Okay, then 2 volts for flange 24 into 24, and 4 volts for web plate 4 into 12 into, sorry, this is in section, then it will 4 into 12 into 24, not in the web plate. Okay, so now we have to reduce to evaluate net area from the grass area. This will 1152, this will 1152. Okay, this was 2 volt, this was 4 volt. You can see, you can watch in the diagram. So it will 9600 minus 1152, it will 8448, and 6076 minus 1152, it will 49.4924. Okay, and net area for the web plate, will be AW divided by 8. AW, what is AW? 1700 into 10 divided by 8. Okay, now we will calculate this also. This is 2833.33. Okay, and it will 2125 15497 and 18509.33. Okay, then what will sigma bt? Sigma bt, which was to find out sigma cbc had find out already, which was 129.47, 129.47, and this was add to with this AF plus AW divided by 6. AF plus AW divided by 6 is 18 509.33 divided by what was this was net area, and it is 1549.7. It also told in design steps completely with the explanation. It will 154 point, so we should not be maximum from 165, and you can see this, you can watch this. This is not maximum, so okay, this is safe. Okay, now we will check for shear stress in tension flange. This is the last stuff in tension flange. Tau Vt will be shear force divided by net area of flange in tension. Okay, flange in tension. From the previous table we can find out net area of the flange in tension, which was 15497. Okay, 15497. And shear force we can obtain shear force 705.53. okay, now we will write here 705.53. okay, we will change this in Newton, so multiply by 20 for the 3. okay, it will 45.52, which should be less than from tau b. Then what is tau b here? Tau b is 0.45 fy. 0.45 fy is to 50, which will 112.5. now you can see this is how much, this is how much. So we can write tau Vt is less than or equal from 112 from 5, which is tau b. okay, now okay, safe. The design have been completed. Please like this video if you don't understand this is good for you. I'm not forcing to like or subscribe, but share to all those persons who are urgently needed for this video. Thank you.